Okay, so hello guys, welcome to another problem solving session with Special Maths Academy. So we're still on our Nigerian Olympiad problem solving series. So today we're looking at problem 3 from the junior competition this time. It says to find the remainder when the 90-digit number 99999, that's 990 times, is divided by 89. Divided by 89. So we're supposed to find this remainder. So first of all, I think generally when you want to find remainders, so many people usually come like this. Long division is usually the way to go. Then you can divide 90 times, and then you get the remainder. But this is not feasible. Why? Because by the time you are done with this, the exams are over actually. You could spend the entire 3 hours, and the chances of you making mistake on a higher level, they're actually very high when you do this. So you don't want to do this. So instead, what I would say, and you should also know that this is not what the organizers want, because if they wanted to divide, they won't give you so many figures. So you don't want to do that. So I think we all agree that long division is not the way we'll be proceeding. So we might want to look for something else. So I want to look at this 99999. Assuming I added 1 to this is something like, let's say it becomes 0. So okay, something like maybe say 999. So assuming I added 1 to this is like 0, right? I carry 1 here is 0, carry that one 0 0 0 0 all the way to the last digit. So just continue carry on to the last one is something like 10. So you see aside, so this becomes like a multiple of 10 if I add 1, right? So that's something you want to look at. Then you should also look at this as well. So a multiple of 10, like not just any multiple of 10, this is actually a power of 10. So that's what you want to look at. Then you should also consider this. If you look at 99 is 100 minus 1, right? Which is 10 to the power 2 minus 1. And 99 has 2 digits, right? And the power of 10 here is 2. So that is 1. Then look at this. 9999 is 1000 minus 1, which is 10 to the power 3 minus 1. So the power here is power 3. And here has 3 digits. So you can still do this. So if you observe, let's 9, if it's 4 nines, this is 10,000 minus 1, which is 10 to the power 4 minus 1. And this is 4 power of 4. And this has 4 digits. So you can see that the number of digits, any 999 number is going to be 1 less than a power of 10. So you can see that this 9999. So if with this, we can, this 90 digits, we can write this as 10 to the power 90 minus 1. So I think we are good on this, right? So we kind of somehow like rewritten the number to be something else. So let me clean this part now. So we're going to use this equivalent form now. It's kind of going to be easier to manipulate from this point. Okay, so 10 to the power 90 minus 1. So we've agreed that is equals to 10 to the power 90 minus 1. So the remainder here, so when I divide this by 89, so instead of divide this by 89, just do, so I'm going to find the remainder now when 10 to the power 90 minus 1 is divided by 89. So this is the new problem now, which is kind of like easier to control. So you know, also from now we're going to use like the knowledge of congruencies like modulo. So you know that assuming I give you something like 6 divided by 4. 6 divided by 4 is 1 remainder 2. And if I write this in the modulo form, this is same thing as saying that 6 is congruent to 2 in mod 4, right? This is like what this means. So this can be read as, so these two are actually like the same thing, they're equivalent. 6 divided by 4, 1 remainder 2 also means that, so the remainder is actually what we're going to put here. So 6 is congruent to 2 in mod 4. So like generally, if you have A is congruent to B in mod C, it means that both A and B leave the same remainder when divided by see, like for example 6 divided by 4 is remainder 2, and 2 divided by 4 is 2. So supposing the remainder now, supposing the remainder 10 to the power 90 minus 1 divided by 89 is remainder arrow, right? Then if I write this in modulo form, this implies that 10 to the power 90 minus 1 is congruent to arrow in mode 89. So I intend to find this arrow now. So this is what I'm going to do. So for this now, you can see 89 is prime. I think this is, we are good on this, right? 89 is a prime number. There are no composite factors for that. The only factors of 89 are 1 and itself. So if you recall, Fermat's little theorem is very clear on this. This theorem states that a to the power p is congruent to a in mode p, provided p is prime, right? This is Fermat's theorem. So in this case, we can just set a as 10 and p as 89, and 89 is prime, so this means that 10 to the power 89 is congruent to 89, is congruent to 10 rather, from Fermat's little theorem in mode 89 Fermat, right? So with that, okay, so that's from Fermat's theorem. And this is Fermat's theorem, yeah. Okay, so let's see. So we know 10 to the power 89 is congruent to 10 with 89. That means 10 to the power 89, when you divide by 89, the remainder is 10. So you know 10 to the power 90 is 10 to the power 89 times 10 raised to the power 1, right? And this 10 to the power 89, we know is remainder 10. This is remainder 10 times 10 in mode 89. That means 10 to the power 90 is congruent to 100 in mode 89. Or rather, when you divide 10 to the power 90 by 89, the remainder is 100. You can still reduce that because that is still big. And if you reduce 100, you have 100 divided by 89 is like 1 remainder 11. So this is like, which is congruent to 11 in mode 89, right? So 10 to the power 90 is congruent to 11 mode 89. So 10 to the power 90 minus 1 will be 11 minus 1, which is 10 in mode 89. So it means that 10 to the power 90 minus 1 is congruent to 10 in mode 89, or rather, when you divide 10 to the power 90 minus 1 by 89, the remainder is 10. So the answer is actually 10, or the remainder is 10. So that's how you solve this. So this is much better than actually going through the long division process. So the main thing was, first of all, writing that number to look like this as 10 to the power 90 minus 1. Then we use Fermat's little theorem, which is like the second part of the problem. So Fermat tore it out then, and voila, we're done. So that's all for this problem solving session. So stick around. Still over HIV, and we're still solving more problems here on SMA. So goodbye for now.